Somewhere on the cold floor of a Martian crater called Jezero, a finger-length core of stone is waiting inside a sealed titanium cylinder, a tube roughly as slender as a stick of chalk. A rover about the size of a small car cut that core loose from a pale outcrop in the back half of 2024. From a slab the mission team had nicknamed Chayava Falls. Threaded through the rock are faint, dark blemishes, little rings and specks that the geologists took to calling poppy seeds and leopard spots. Find that same speckling in a stone on our own world, and a textbook would tell you, almost without pausing, that something alive once rested there and quietly rearranged the chemistry around it. After about a year of argument and cross-checking, the agency settled on a phrase chosen with enormous care. The sample holds what they describe as a potential biosignature. The word potential is doing a great deal of work in that sentence. Nobody with a reputation to guard is saying the word life. Not yet, and perhaps not for a long while. Yet the tube remains exactly where the rover left it, resting on the skin of a planet that went still something like 3.5 billion years in the past, and the soonest any human hand might hold it is somewhere in the closing years of the 2030s, after a sample return mission that does not yet fully exist. This is a story about that rock, but it will not stay with that rock, because the dry world we call Mars is not the only world to have died, and it may not even be an unusual one. The quiet thought worth settling into, the one most conversations hurry past because it makes people uneasy, is not whether life can get started somewhere out in the dark. It is whether life, once it has started, can hold on. The longer scientists study what is genuinely required to hold a planet livable, the more the real puzzle seems to move. The hard part may never have been the beginning. The hard part may be the lasting. Consider the bare arithmetic of what has been counted. As of the early weeks of 2026, the official ledger of worlds confirmed beyond our own sun, kept in the NASA Exoplanet Archive, stands at 6,087. The 6,000th was logged back in the autumn of 2025. Set that against the roughly 195 sovereign nations on Earth, and you find we have now charted more planets around other stars than there are countries underfoot, by a factor of about 30. And those are merely the ones a telescope has actually pinned down. The estimated total is a different order of thing entirely. The Milky Way holds on the order of 200 billion stars, and the working assumption, assembled from the yield of the Kepler and TESS surveys, holds that almost every one of those stars keeps at least a single planet, many of them a whole retinue. Run that multiplication out, and you arrive at a number with 12 digits in it, hundreds of billions of worlds inside this one galaxy. Of those, the most recent estimates place the count sitting inside the so-called habitable zone, the ring of orbital distances around a star where water might, in theory, stay liquid wherever it gathers, a tally that runs into the tens of billions. 10, perhaps 100 billion plausible homes. So why does the sky stay so silent? The first thing to take apart is that comforting phrase, the habitable zone, sometimes called the Goldilocks zone. It promises far less than it seems to. All it really claims is that, in theory, water might keep from freezing or boiling there. It does not say water is present. It does not say water was ever present. It does not promise the planet kept an atmosphere thick enough to hold an ocean, or that the surface today sits anywhere near the temperature at which water stays a liquid. It marks an orbit at about the correct remove from its star, and not a single thing past that. So when you hear that this galaxy may carry 10 or 100 billion planets inside that temperate band, the honest reading is plainer. That many orbital slots exist where life has not yet been positively excluded. 1,000 other conditions can still exclude it, and very often do. Look at the catalog we actually have, and the disappointment sets in fast. Most of those 6,000 worlds resemble Earth not at all. The earliest ones found were hot Jupiters, giant balls of gas swung so near their parent stars that the outer air glows and streams off into space. They were spotted first only because they are the easiest things to see. After them came the super-Earths, rocky worlds heavier and broader than ours, many of them racing their suns on orbits wound so tight that a full year there is finished inside a handful of our days. Then came the tidally locked worlds, planets pinned so that one face stares at the star forever, while the other is turned eternally into the dark. One hemisphere baked hard, the other so frozen that the very air can drift down as snow. Then the scorched orbits, the worlds stripped of their air, the worlds where gravity presses so hard a human heart could not keep pumping blood against it. When you sort the whole inventory honestly, the planets that look like Earth in any way that matters, about Earth's size, parked at about the right distance, circling a fairly calm star, number only in the low dozens. The famous few have names now, worlds like Kepler 186f and Kepler 452b, and the 7 tight planets of TRAPPIST-1, 4 of which graze that temperate band. Even Proxima Centauri b, the nearest of them all, only 4 light-years off, sits in its star's habitable zone, though that star is a small red dwarf prone to violent flares, and most stars in the galaxy are exactly that kind. So a large share of the silence explains itself. The bulk of them were never going to reply to anyone. They simply could not. They lack the chemistry, the warmth, the air, the steadiness, the time. They are stones turning in the cold. But that is the easy part of the silence. The genuinely strange part is not the worlds that could never have lived. It is the worlds that, just possibly, once could have. The Earth-resembling candidates genuinely exist in non-trivial quantities, even on the stingiest reckoning, and from every last one of them comes the very same thing. No radio call, no flash of light, no chemical fingerprint anyone can confidently read as life. Nothing at all. That is the silence that resists easy explanation, the hush of the worlds that, by any reasonable statistical guess, ought to have had something living on them. Here is an image to hold while we walk through the rest. Imagine a long, dark coastline seen from a boat far offshore at night. Once, you are told, there were houses all along that shore, lamps in the windows, people at the tables, smoke from the chimneys. Now you drift past in the dark, and almost every window is black. Here and there, very rarely, a single lamp still burns, but it is so far off, and the cold water between you and it is so wide that you cannot tell whether anyone is still tending it or whether the lamp simply hasn't gone out yet. The coastline was not always dark. Somebody lit it, but it has been a long time, and the lights have been going out one by one, and what reaches you across the water is mostly the memory of a glow. That is closer to what the instruments actually do. When the Kepler telescope found a planet, what it truly recorded was a star dimming by a sliver, on a steady, repeating schedule every few days or weeks. The dip is the planet sliding across the face of its star and blocking a thread of the light. That dip is all there is for most of them. We almost never see the planet itself. We see a faint, regular shadow, and from the shape and the timing of that shadow, we reason out how large the world is, how close it orbits, how long its year runs. We do not see what is there. We register only that something is present, and the telescope then slides on to the next star and the next faint shadow thrown on the wall. If lying here in the dark and turning a vast, quiet question over in your mind is the kind of thing that loosens the day's grip and lets the body grow heavy, then you might let this small corner of the night know with a gentle tap, or leave a soft word below for whoever else is lying awake tonight under the same enormous sky, asking the same things. It costs you nothing, and it helps these slow wanderings drift toward the people who need them most. But there is nothing to do just now, and nowhere at all you have to be. So let the thought keep unspooling, and let yourself unspool gently along with it. You can guess the shape of the houses from far out on the water, but you cannot step inside, and you almost never learn whether anyone was ever home to light the lamp. The second thing the silence is made of is not distance. It is timing. Suppose, generously, that every roughly Earth-like world out there did grow something clever, something that built and wondered and sent signals.
The likelihood that any two such civilizations would be awake in the very same stretch of time, inside a galaxy whose story already runs past 10 billion years, is faint. Our own radio chatter has existed for roughly a century. Anything we would recognize as human civilization reaches back perhaps 10,000 years. People shaped anatomically like us go back something on the order of 300,000. And the planet beneath all of that has been fit for living on for close to 4 billion years. Try shrinking that long, livable history down to a single year on a wall calendar. On that scale, the entire run of humankind flickers into being only in the last minute and a half before the final midnight. And everything we would call modern science, telescopes, radios, spacecraft, occupies the closing second. Now hang a separate calendar on the wall for every habitable world in the galaxy. Each was started at a different moment and will come down at a different one. And on nearly all of them, the bulk of the year is quiet. Just weather and slow chemistry, and nothing that calls out. Only a few stray seconds anywhere on any calendar carry anything loud. For two worlds to be loud during the same few seconds, their calendars lined up just so, is a long shot. Reach blindly into the galaxy, and the world you close your hand around has most likely not begun its noisy stretch yet, or finished it ages back, or never had one to begin with. A silent sky is not evidence of an empty one. It is evidence about clocks that rarely chime together.
There is a half-wry name some astronomers give to this hush, the Great Quiet. They take care to keep it apart from the Great Filter, a separate idea about what might cut young civilizations short before they ever spread. The Great Quiet claims nothing so dramatic. It is only the plain report of the listening. The antenna is switched on, and has been for as long as we have owned one, while the level of anything resembling a deliberate signal sits, stubbornly, at essentially nothing. Part of that hush may genuinely be that no one is there. A good part of it, though, is almost surely the hush of someone who once was there and is not any longer. The dark coast is real. The houses stand, the windows are unlit, and whether a single soul still moves behind any of them is a question we do not yet own an instrument fine enough to settle. What we do hold is a steadily sharpening sense of how long that shoreline runs and how many houses it once held. If you want to walk up to one of those darkened houses and press your face to the glass, you do not have to cross any great gulf. There is one next door. Mars is the simplest dead world to reckon with, because it hangs there in plain sight. On the right clear night you can step out, find the small, unwavering, rust-colored point low among the stars, and there it sits, the fourth world counting outward from the sun, a neighbor you never have to imagine because it is simply there.
Across almost the whole of human history, that point was just a roaming light and the name of a war god. It turned into a place only in the closing decades of the 19th century, when lenses grew sharp enough to reveal a disk with white caps that swelled and shrank by season, and dim regions a few observers talked themselves into reading as forests. In that same era, the Italian astronomer Giovanni Schiaparelli logged long, straight grooves across the surface, and the American Percival Lowell, gazing through his Arizona telescope, persuaded himself they were canals, cut by a parched civilization to carry its last water down from the icy poles toward the warmer middle of the world. None of it held up. The straight lines were the eye stitching order onto a blurry smear. The
The dark regions were drifts of dust and bare stone. There were no canals, and Mariner 4's 1965 flyby sent home close pictures of a cratered desert that ended the dream. And yet, the deeper hunch, Mars as a world in the act of dying, turned out to be nearer the truth than its inventors knew. The Mars we actually have is, by any sensible standard, a corpse. The average surface temperature sits near minus 63 degrees Celsius, roughly the coldest reading ever logged in Antarctica, save that, on Mars, that brutal number is the ordinary day rather than the rare extreme. The air is so sparse that open water on the ground would boil and freeze almost in the same breath, the pressure too feeble to let it stay liquid at all. Stand there in a flawless suit, and the chill would still seep up through your boot soles in a matter of minutes. Above you, the sky would glow a pale butterscotch rather than blue, because there simply is not enough air to scatter sunlight the way ours does. The sun, once you found it, would look shrunken and faint, and the close horizon would fall away fast under a gravity barely a third of Earth's. It has the unmistakable feel of somewhere a living thing once inhabited. That feeling happens to be exactly right. Here is the bones of it. Mars once carried a magnetic field, a true one, wrapped around the whole planet, churned up by a molten metal core turning at its heart, exactly as Earth's core turns now. That field worked as a shield. It turned aside the solar wind, the ceaseless spray of charged particles the sun flings out in every direction. With the shield up, whatever air Mars owned, it could keep. Water on the ground could remain water. The sky could stay thick enough to read as a real sky. Then the shield failed. The best current estimate, drawn from the magnetism frozen into Martian meteorites and from orbital surveys of the crust, is that the planet's global field gave out somewhere around 3.9 billion years ago. The exact date has been tugged back and forth by recent work. A closely watched Harvard study published in 2023, backed up by follow-on papers through 2025, hints the field may have lingered a touch longer than the old consensus allowed. But the headline never changes. The core cooled, the internal dynamo stalled, and the shield was gone. After that, the air began to leak away, not in one catastrophe, but grain by grain. Over the next several 100 million years, the solar wind nibbled at the top of the atmosphere, flicking the lighter molecules off into the dark one by one, so gradually that no single human lifetime would have caught any of it happening. The orbiting MAVEN spacecraft, which reached Mars in 2014, has actually caught this theft in progress and clocked the rate. The trouble was simply that the ledger ran red. More air departed than anything could resupply, and in the end, the account emptied. Today, the surface pressure sits between roughly 1 and 14 millibars, depending on where and when you measure, against Earth's 1,013, which leaves Mars with under 100th of the air we stand in. To find anything that thin here, you would have to climb some 30 kilometers up, about 3 times the cruising height of an airliner. That is the air Mars hands you at ground level today. And yet, a window did open once. It stayed open a long while, and during that long while, things happened. The Curiosity rover, set down inside Gale Crater back in 2012, has by now spent over a decade grinding slowly up the flanks of a 5-kilometer mound at the crater's center, a peak named Aeolus Mons, reading the stone bed by bed. Gale was a lake. We are sure of that today. The bedded mudstones, the pebbles rounded by running water, the beds of salt, the clays that take shape only in standing pools. All of it spells the same sentence. Around 3.8 billion years ago, this patch of Mars brimmed with liquid water, a deep lake with rivers feeding into it, and it lingered. The minerals say it held on, off and on, for something close to 700 million years, the last plainly livable conditions guttering out near 3.1 billion years back. 700 million years is almost impossible to truly feel. Complex life on Earth, anything you would recognize as an animal, has only been around for about 600 million. The Cambrian burst that first crowded the rocks with hard-shelled creatures came roughly 540 million years ago. Which means the stretch during which the Martian surface was fit for life outran the whole career of complex animals on Earth to date. And here, in those very same ages, life had already taken hold. The earliest convincing trace of it, of single-celled organisms, turns up in our own rocks at roughly 3.5 billion years, with contested but genuine hints of biology reaching back nearer 3.8 or 3.9. Line those dates up, and something striking falls out. The two neighboring planets were running the very same trial at the very same hour of cosmic history. Both held standing water in the same epoch. Both wore real atmospheres in the same epoch. One of them, beyond any doubt, kindled life. The other arrived at the starting line carrying every ingredient needed to do the identical thing. And then, around 3 billion years back, the welcome on Mars wore out. Which carries us back to the tube. Perseverance, the car-sized rover that touched down in Jezero Crater during February 2021, with the little helicopter Ingenuity folded beneath it, was sent to one place for one reason. Jezero, like Gale before it, had once been a lake. Look at the orbital photographs and you can trace the petrified fan of an old river delta, where water spilled down out of the surrounding highlands and laid its sediment down in spreading tongues. Hunting for chemical traces of biology was the entire point of the mission, and the rover has been crossing that dried delta and caching cores ever since it landed. In July of 2024, it pressed its drill into a pale slab the team christened Chayava Falls and pulled out a finger of rock, sealing it inside a tube they labeled Sapphire Canyon. Almost at once, something caught the scientists' eyes. Scattered through the sediment were small, dark nodules, arranged in a way that, on Earth, would raise eyebrows, some like poppy seeds, some like the dappling on a leopard's coat. When the rover turned its onboard instruments on those specks, the chemistry came back as iron phosphate in the mineral called vivianite, paired with iron sulfide in the mineral called greigite. On our own planet, that pairing means something. Vivianite and greigite, sitting beside organic carbon in mudstone, laid out in those exact freckled patterns, are the kind of leftovers certain microbes produce when they go about their living. In particular, the iron-breathing bacteria that wring energy from buried sediment by shuttling electrons back and forth between iron and sulfur. What Perseverance had photographed in that core is precisely what a textbook would file under microbial signature. The study laying it all out reached the pages of Nature in September 2025, following a full year of grinding review inside and outside the team, and the authors weigh every word like jewelers. The term they settle on is potential biosignature. They lay the rival stories on the table beside it. The same freckling could, in principle, be cooked up by chemistry with no connection at all to life, by certain volcanic reactions, by water working slowly on rock with no living thing involved. They do not announce life on Mars. They announce that they have found the one feature that, encountered on Earth, you would point to first as a fingerprint of life, while admitting the other explanations have not been ruled out. And the rock itself is still up there, resting in its sealed tube on the Martian ground. The plan meant to carry it home, the Mars Sample Return Effort, a venture shared with the European Space Agency that would deliver the core to laboratories able to run tests no rover could dream of, is presently in upheaval. The early timetable has dissolved into budget reviews and arguments over how to rebuild the whole architecture more cheaply. The latest honest guess for retrieval lands somewhere in the late 2030s, quite possibly later, which means the single most important stone our species has ever identified is going to wait on the surface of another world for another decade or more, while we work out how to go and fetch it. Until then, All we are holding is the picture. There is an old thought about photographs, that they are less portraits of people than portraits of instants. The face you photograph today keeps on aging. The sliver of time pinned to the film does not. You are left clutching a small rectangle that is a fragment of a moment, cut loose from the person who lived it. That is what the Chayava Falls core is, a fragment of a moment, perhaps a fragment of Martian time in which something was alive. Or perhaps a fragment of Martian time in which nothing ever lived, and stone merely arranged itself, by accident, into shapes that life would have left behind. We cannot yet say. The image itself is real. What it depicts is still being argued out. If you have ever bought a house that other people lived in before you and gone climbing up into the attic, you will recognize the feeling waiting there. There is a shoebox in the rafters. Inside are photographs, real ones, real faces, strangers in clothes that date them, standing in rooms you half recognize as your own, in a life that ran through your hallway and your kitchen long before you signed the deed. They are not your relatives. They are simply people, doing ordinary things in the very space you now occupy, and the first time it truly lands, it is difficult to hold steady. Mars is that attic. You haul yourself up expecting cobwebs and bare rafters, and instead your hand closes on a photo album. Every print in it is genuine, each showing someone you will never meet, and the camera that made them quit working an unthinkably long time ago. That core in the tube is only the most recent print pulled from the box. There are surely others. The mission that found it is one of dozens, on the ground and in orbit, that have studied this planet across 60 years of knocking. Now and then the door rattles in its frame. Now and then a shutter lifts. Mostly the house stays silent, the wind dragging red dust across the boards, and the porch lamp left burning over an empty step. Mars is the obvious corpse, the harder one to face, because it is far more truly our double, is the world that sits on our other side, the one most people breeze past in school and shelve under hot rock without a second glance. That is Venus. We simply do not picture Venus the way we picture Mars. Mars soaks up all the attention. The rover planet, the colony planet, the one painted on magazine covers beside a square-jawed figure in a spacesuit. Venus gets perhaps a week of class time, introduced as the runaway greenhouse world, the cautionary tale, the planet that ran too hot, and then the lesson moves along. That framing is wrong, or at the least it leaves out the part that matters most. On paper, Venus is Earth, very nearly to the decimal. It carries close to the same width across, close to the same mass, close to the same density, and it congealed out of the same swirling disk of debris at about the same moment, drawn from the same general pantry of materials. It rides in the inner solar system. By every yardstick astronomers once meant when they said sister world, it is ours. Hand a stranger the bare specification sheets of two planets, one marked Earth and one marked Venus, and ask which supports life, and they would have no honest way to choose. Here is the part worth genuinely sitting with for a minute or two. Venus, it turns out, may once have been livable, with open oceans of liquid water across its surface, for as much as 2 or 3 billion years. That is not idle daydreaming. It is the verdict of climate simulations run at the Goddard Institute for Space Studies in New York, a NASA lab. The work led by Way and Del Genio, first released in 2016 and sharpened in the papers that followed. They take the best reconstruction of early Venusian conditions, push a full 3-dimensional climate model forward through deep time, and they find that, given reasonable guesses about cloud cover and the planet's slow backward spin, a single Venusian day now stretching longer than its year, Venus could have held a steady temperate climate, oceans and all, across some 2 or 3 billion years before it toppled into the inferno it has become. Set that against the clock of complex life on Earth, which in any form richer than a single cell has only run about 600 million years. And the comparison is staggering. Venus, on this reading, kept surface oceans for roughly 5 times longer than animals have existed here at all. There was on that planet an environment any reasonable person would have called habitable, lasting a span that dwarfs the entire career of every creature anyone has ever given a name. Whether a single living thing ever made use of it is a wholly separate question. We hold no fossils from that planet's surface at all. To this day, not a single sample of Venusian ground has ever been carried home. The handful of Soviet landers that managed to set down there across the 1970s and the opening years of the 1980s survived, on average, under 2 hours apiece before the heat and the crushing weight finished them. The toughest of them, Venera 13, held out a little past the 2-hour mark in 1982, long enough to radio back the first color panorama ever taken from another planet's surface. A flat, tan spread of cracked slabs, the sky above it a heavy sulfur yellow, and not a leaf, not an animal, certainly nothing that ever built anything. But the live question was never what stands there today. The live question is what may have stood there 2 billion years earlier, when the place could have worn an entirely different face. Then, roughly 700 million years ago, Venus turned. What pulled the trigger is still argued over. Among the frontrunners is a planet-wide resurfacing, the entire crust repaved by volcanism inside a startlingly brief geological window of perhaps 50 to 100 million years. Alongside it, the sun's own gradual brightening, a star that has been climbing in luminosity by something like 1/10 every billion years across its lifetime, and the chance of a violent bout of volcanic outgassing that flooded the air with carbon dioxide in a geological eye blink. Perhaps several of these struck at once and shoved the climate past a line it could no longer walk back from. Whatever lit the fuse, the climate inverted. Water vapor is itself a fierce heat-trapping gas, so as it filled the sky, it held in more warmth. The warmer air carried still more vapor, which held in still more warmth, and the oceans began to steam away. And the more they steamed, the hotter it grew. And the hotter it grew, the faster they steamed. That self-feeding spiral is what the word runaway is doing in Runaway Greenhouse. By the time it had run its course, every ocean on Venus was gone. High up, solar ultraviolet tore the water molecules apart. The feather-light hydrogen drifted off into space. The heavier oxygen mostly latched onto surface minerals and was sealed into stone. And the carbon dioxide that had once been dissolved in seawater and bound up in rock was now loose in the air, and the air simply went on thickening. What it thickened into is a furnace. The surface of Venus now averages around 462 degrees Celsius, in the neighborhood of 860 Fahrenheit, hot enough to pour lead into a puddle. You do not have to picture standing on it, because you would never get to stand on it. You would be dead inside a second. The weight of the atmosphere runs to about 92 times what presses on us at sea level, the same squeeze you would feel beneath roughly 900 meters of seawater, not 9 of them, but 900, deeper than any crewed submarine has ever carried anyone. The Soviet probes that lasted those few hours managed it only because they were built, in effect, as deep-sea diving bells, their hulls cast thick in titanium to bear the heft of an ocean of air. Overhead, if you could somehow make it out through the murk, hangs a yellow gloom of clouds spun from sulfuric acid. Those clouds do rain, but the rain never lands. It boils back into vapor partway down, because the lower air is far too hot to let liquid acid stay liquid. So the sky keeps its weather, and the weather keeps its acid, and the acid never touches the ground. There is a homely picture I keep returning to for this, one almost everyone has lived through. You set a pot on the stove to boil, click the burner on, and wander off, meaning to come back when it does. Then the phone rings, or someone is at the door, and the pot slips your mind. When you finally remember and walk back in, the base of the pot is glowing dull red, and every drop of water is gone. That is Venus. For a long stretch, the pot sat fine, and the water inside merely simmered. You could still see its surface, still see the metal beneath, still cook a meal in it. Then, by slow degrees, the level sank. Then the pot ran dry. Then the pot began to glow. Venus has been a glowing, empty pot for 700 million years, and there is no hand coming to switch the burner off. Here is what tips Venus, for me, into the harder of the two worlds to dwell on. When oceans die, they do not vanish without a word. They leave a mark. Aim a sensitive enough instrument at the upper air of Venus and weigh the proportions of two flavors of hydrogen, and you turn up a number that makes no sense unless this planet once held vastly more water than it now does. Ordinary hydrogen carries a single proton in its nucleus. Its heavy cousin, deuterium, carries a proton and a neutron, and it is scarce. Only about 1 part in 6,400 of the hydrogen in Earth's seas. On Venus, the share of deuterium against ordinary hydrogen comes out near 150 times the earthly figure, a ratio first pinned down by the Pioneer Venus probe back in 1978. That is not a modest discrepancy. It is the sort of lopsided number that admits only one decent reading. Lighter hydrogen slips away to space more readily than the heavy kind, because at any given temperature, the lighter a thing is, the faster it moves, and the swiftest things at the top of an atmosphere are exactly the ones the solar wind and ultraviolet light peel off and lose. So take a world that began with both kinds of hydrogen blended through its oceans. Boil those oceans up into the high air, and let a few billion years of sunlight pick at the vapor. The common hydrogen is stripped off the quicker, and the deuterium loiters behind. As the ages pass, the balance of heavy to light in what remains keeps climbing. Read 150 times Earth's ratio in the Venusian sky today, and what you are reading is the chemical signature of a whole ocean that simmered off into space ages ago. Its lighter half carried away first, its heavier half left hanging in the sky. The ocean itself is gone. The record of it is not. Sit with that for a moment, and a strange grief comes with it. We do not usually grant planets ghosts, yet Venus has one. And it is chemical, it is measurable, it is genuinely there. The ocean that once lay across Venus is, in a real and literal sense, still suspended overhead, only now as a ratio of isotopes, a figure on a spectrometer, the exact shape of an absence. And here is the turn that matters. We could pick that ratio out from a great distance. Set a Venus like this around some other star 60 light-years off, point the right instrument at it, and we could measure the deuterium mark in its atmosphere and declare, with real confidence, that this world once held abundant water and holds it no more. We could say so without ever setting out, without ever dropping a single lander. We could read its obituary from clear across the dark. There may well be worlds out there, this very night, on which we have already done exactly that, and simply not grasped what we were seeing. The instruments able to read this reliably across light years are only now switching on. The James Webb Space Telescope already aloft, and a generation of giant ground observatories. The 39-meter extremely large telescope rising in the Chilean desert among them, arriving across the late 2020s and on into the 2030s. The first time we recognize a Venus-like ghost in an exoplanet's air, it will not really be a discovery. It will be a confirmation of something the universe has been quietly recording all on its own, the leftover trace of an ocean that used to be. Venus, too, has left its porch light burning. The light has burned for 4 billion years now. The house behind it burned down long ago. So we are left with 2 dead worlds inside our own small neighborhood. Mars, undone by a core that cooled and an atmosphere that fled. Venus, undone by a greenhouse that ran away with itself, and a whole ocean cooked off into the sky. Two different deaths, the same silence at the end. Two planets of the same age, the same stock of materials, the same build, the same opening conditions. One cooked in the fire, one buried in the cold, and our own world threaded between them, which forces a question that ought to unsettle anyone willing to hold it. If two of the three stony planets that began their lives inside the sun's temperate band have each lost the gift already, by two entirely unrelated routes, then how secure is any such window, anywhere? And what does that say about the third planet, the one still keeping its lights on? That is the next place to look, because it turns out the temperate band is not a plot of ground you can drive a stake into and settle for good. It drifts. The first time most people meet the idea of a habitable zone, the picture that lodges in the mind is a fixed neighborhood. You imagine a ring drawn around a star. Inside the ring, everything is just so. Outside, it is not. The worlds within are the lucky ones. The worlds beyond are scorched or frozen. Earth happens to lie inside the ring, which is why we are here, and that is more or less the whole tale. Nearly all of that is mistaken. The zone is genuine enough, and the arithmetic under it is sound. It is, very precisely, the span of orbital distances around a star at which water could keep to its liquid form on a surface, granting some basic assumptions about a planet's air and how much light it throws back. For our own sun, the most widely used estimates, going back to the classic work of James Casting in the early 1990s, place that band today between roughly 95% of Earth's orbital radius and about 170% of it, with the conservative and optimistic edges shifting a little depending on what each model supposes about clouds and the makeup of the air. But that band will not hold still, and the reason is simple. Stars themselves do not hold still. To us, a star looks like the very emblem of constancy, only because our lives are brief and a star's changes are vast and slow. Stretch the view across billions of years, and every star brightens, cools, swells, and in the end, dies. The brightening is what concerns us here. A star on the main sequence, the everyday kind our sun is, and the kind most stars across the galaxy happen to be at any moment, grows steadily more luminous as it ages. In its core, hydrogen fuses into helium. The core packs down a little denser. The pressure climbs, the temperature climbs, the rate of fusion climbs, and the star pours out more energy. From one year to the next, the rise is invisible. Across deep time, it mounts up. Our sun burns about 30% brighter now than it did when the Earth first took shape, and that is no trifling tweak. It is the gap between a pleasant room and a raging fever. Were today's sun as dim as the one Earth was born under, our planet would be a frozen marble. There is a famous wrinkle folded into this, the faint young sun paradox, a stately way of noting that the infant sun shone far more weakly, and yet the rocks carry unmistakable proof of open water on the young Earth's surface as deep as 4 billion years back. Somehow that early world stayed warm enough for seas while catching much less sunlight than we now enjoy. And the likeliest answer is a far thicker blanket of greenhouse gases in those days, heavy with carbon dioxide and methane, hoarding the heat. The point that matters for us is simply the climb. The sun has strengthened by roughly a third across 4.5 billion years, and it is strengthening yet. At present, by something near a tenth every billion years, which sounds gentle, the way almost everything sounds gentle on that clock, and whose effect on Earth's climate is anything but gentle. As the sun brightens, the temperate band slides outward. The distance at which water can stay liquid is pushed ever farther from the star, and the inner boundary, the line past which any reasonable atmosphere would let the seas boil off, creeps outward season upon season. For now, the Earth rides comfortably within the band. The inner edge still lies somewhere sunward of us. In about 1 billion years,
give or take some hundreds of millions according to whose model you trust, that inner edge will arrive at Earth's orbit. That is not, in itself, the abrupt end of life here. The machinery grinds slower and crueler than that. As the sun's output mounts, the surface warms. The warmer surface drives more water up into the high air. Ultraviolet light shatters that vapor, and the freed hydrogen leaks away to space, the very same script that ran on Venus. The oceans begin to thin, the surface chemistry begins to turn, and the kind of life that demands complex bodies and steady temperatures and oxygen and standing water all at once begins to run out of room. Most credible models gather around a figure of roughly 1 billion to 1.5 billion years out before complex life on Earth is no longer tenable. Microbes may cling on longer. Microbes are formidable. Even today, there are organisms going calmly about their lives at temperatures hotter than the point at which pure water boils. One heat-loving strain pulled from a deep-sea vent thrives at 121 degrees Celsius, in conditions that would erase nearly every other living thing we know of. A little of that hardy life might outlast the collapse of the larger living world. But the planet we actually inhabit, the one with its forests and seas, its animals, its rain and snow and turning seasons, has something like 1 billion good years remaining. Push the clock further and it only darkens. In roughly 5 billion years, the sun will burn through the last hydrogen in its core and swell into its red giant phase. Its outer shells will balloon outward, hundreds of times its present width. And although the surface of that bloated star will actually cool a touch, its total output will leap by a factor near 1,000. The inner planets will find themselves inside the swelling solar atmosphere. Mercury will be swallowed. Venus will be swallowed. The Earth, by the most careful modeling of the past few years, will most likely be swallowed as well, somewhere around 7.5 billion years from now, though the Sun's own loss of mass will widen the planet's orbits and let a few scenarios leave the Earth barely outside the fire, scorched but not devoured. The central estimate, though, is that the Earth is eaten, and what remains of the Sun afterward will settle into a slowly cooling white dwarf no larger than our planet is now. So the world itself carries an expiry date, and the world's habitability carries a different, far earlier one. The way I have come to hold all this is that the temperate band is not a place at all. It is a moment. Picture a patch of late afternoon sun lying across the floor of a room. You have pulled a chair into it to read by its warmth, and for a while, it is perfect. But the patch is moving, slow as the turning planet that makes it, sliding steadily across the boards toward the far wall. You can keep reading only as long as you sit within the light, and the light will not wait for you. Worlds sit in that traveling patch, one after another. The bright square crossed off Mars's place on the floor something like 3.5 billion years ago. It slid past Venus's place around 700 million years back. Right now, it rests squarely on the Earth, and we are reading by it, and it feels, as such light always does, permanent. It is not. The patch keeps gliding, the warm boards behind it keep going cold, and out among other stars, there are surely worlds the light has already left. Planets we still file under the habitable zone of suns that have shone for many billions of years now, and done their long brightening, and may, by this point, have shoved their own warm band clean past by those worlds. We spot them, we enter them in the catalog, and we jot beside them that water could run liquid there. The reality is knottier. Water could run liquid there if the conditions happen to be exactly right in the instant we glance. What they were 1 billion years before our glance may have been wholly other. What they will be 1 billion years after it most certainly will be. We are reading a single, still frame. The frame says nothing about how long the scene has held that shape, nor how much longer it will. The temperate band, put plainly,
hides a time problem that we tend to wave away whenever we discuss it. A world lies in the band now. That is no promise it always did. It is no promise it always shall. It is not even a hint that anything ever lived there across its whole long history. The label smells of permanence that the physics never signed off on. There is a companion point worth dwelling on. In most models, the temperate band is worked out on the assumption that a planet wears an atmosphere much like Earth's. It assumes a magnetic field. It assumes a steady spin. It assumes the world arrived with water in the first place. Not one of those is a given. Heaps of planets inside the band own none of them. Heaps of planets outside the band today may have owned each of those things at some earlier stretch of their past. The phrase is shorthand for something far naughtier than it lets on, and the shorthand can deceive. What holds true is that a playable range exists for any star at any given hour. What also holds true is that the range glides as the ages pass, and the worlds it glides across are not the same worlds from one epoch of a star's life to the next. A planet that is a flawless candidate today might be a sheet of ice a billion years on, once its star has faded by just enough to draw the band inward. A planet locked in ice today might warm into welcome a billion years hence, as its star kindles enough to thaw it. The galaxy is crowded with worlds in the wrong spot at the wrong hour. That is the part that sticks in the throat. There are surely planets out there whose finest age came and went a billion years ago and squandered all they might have been. There are surely planets whose finest age has not begun and will not for another billion years. The count of worlds that happen to be living their habitable age at this exact moment is a thin slice of the whole. We are one of that slice. The window stands open here. The window stands shut almost everywhere else. And that is reckoning only with our own star, a placid, well-mannered yellow dwarf, ladling out its energy at an even rate with scarcely an outburst and lasting a very long while. By the measure of stars, the sun is an easy neighbor. Most stars in the galaxy are nothing of the kind. Most are smaller, redder, and far less forgiving toward the worlds that circle them. The great majority of the planets we have turned up, the ones sitting in that so-called temperate band, ride around stars unlike our own, stars that on their gentlest day are merely violent, and on a rough day are something worse. And from a certain angle, every day on such a star reads as a rough one. That is where the search must turn next, because most of the tickets we hold in this lottery are not the kind that pay out the way the daydream promises. When most people imagine a star ringed by planets, they imagine the sun, a yellowish, even-keeled body hanging at the center of things, shedding a comfortable wash of light, doing its work without a fuss. That is what a star is meant to look like in the picture we carry, the star you put behind an alien beach when you imagine alien sunlight. It is not how most stars actually look. Something like 3 of every 4 stars across the Milky Way belongs to a class called the M dwarf, the red dwarf. These are little stars, far slighter than the sun, running from about half its mass down to a mere 8% of it. They burn cooler, their surfaces somewhere between roughly 2400 and 3700 Kelvin against the sun's 5800. And because they run cool, they spill most of their light into the infrared, the visible part of it tilted toward red, which is how they earned the name. They are faint, they are small, and were you to swap one in for the sun, the inner solar system would lie in a perpetual dusk. They are also, by a wide stretch, the commonest star there is. 3 in 4 of every star you could ever sail to in this galaxy is a red dwarf. 3 in 4 of the temperate bands under study right now wrap around red dwarfs. The overwhelming share of those headlines about an Earth-sized world in the habitable zone are describing planets bound to red dwarfs. So whenever we tally how many livable worlds might be scattered out there, we are talking by default mostly about red dwarfs. The arithmetic simply falls that way. And it matters because red dwarfs are anything but gentle. Here is the bit that needs a while to settle in. Small stars like these carry a handful of traits that look, at first, like kindnesses to life.
They live enormously long because they sip their fuel rather than gulp it. The smallest are expected to shine for trillions of years, vastly outrunning the entire present age of the universe. They hold their output steady across those immense lifetimes. Their temperate bands are drawn in small and close, so that a planet placed to catch an Earth-like ration of warmth from a red dwarf must huddle in very near, nearer to its star than Mercury sits to the Sun, so close that gravity usually locks one face toward the fire forever. The orbits are quick. A year on such a world might run anywhere from several days to a couple of weeks. Such worlds are easier to catch, too, because they cross their stars often, handing us transit after transit to watch, and the signal is bolder, since a planet blots out a larger bite of a small star's light. Every bit of that is the encouraging side. The grim side: red dwarfs run magnetically savage. Smaller stars tend to seethe with more magnetic activity than larger ones, fiercest of all when they are young, throwing more spots across their faces and far more flares. A red dwarf's flares can run, in the worst cases, 10,000 times stronger than the mightiest flare our own sun has ever been caught producing. To set the scale, the strongest solar storm in recorded history, the Carrington event of 1859, merely set telegraph wires sparking. A comparable flare on the sun would briefly drop radio links across half the Earth, while the same event on a red dwarf would wash the whole inner system in radiation at doses no biology we know could ride out unshielded. And these are not freak occurrences on a red dwarf. They are the routine. Over many such years, the flares can scour a close planet's atmosphere away entirely, the high-energy radiation boiling it off into space. Take TRAPPIST-1, 40 light-years off in the constellation Aquarius, and among the most exhaustively studied red dwarf systems we possess. It holds 7 Earth-sized planets, several parked in the conventional temperate band of their star, a roughly 7.5 billion-year-old ember. It is one of the marquee systems of the whole field. 7 rocky worlds, more than one of them able, in principle, to hold liquid water, circling a single nearby star. On paper, it is precisely the address you would scout for life, with TRAPPIST-1e the favorite of the bunch. Then in 2025, the James Webb Telescope watched the stars flaring across a sustained stretch and clocked it throwing roughly 6 flares a day. 6 a day. That tallies to well over 2,000 flares a year, year upon year, across billions of years. The worlds in that temperate band, tucked nearer to their star than Mercury sits to the Sun, take every one of those flares square in the face, stripped of the cushion that distance would lend them. Picture a small child set down directly in front of a towering stage loudspeaker with the bass cranked to the very top of the dial. And the dial has stood at the top since the system was born, and it will hold there for whatever life the star has left, which amounts, in other words, to trillions of years. What does a barrage like that do to a world? Laboratories have tried to act it out. Researchers have taken cultures of assorted Earth microbes, among them the toughest radiation eaters we know of, such as a bacterium called Deinococcus radiodurans, nicknamed Conan the Bacterium, which shrugs off doses thousands of times past what would drop a human on the spot. And they have dosed those cultures with mock flare radiation of the red dwarf kind, at the strengths the TRAPPIST-1 worlds would genuinely absorb. The verdicts differ from study to study. The broad finding, though, is that flaring on this scale, recurring at this rhythm, is enough to scrub all but the most stubborn microbes off any exposed ground. Whatever sits in shallow pools, in topsoil, out under open air, gets cooked. A little life might endure deep below the rock, in caves, in dark seas beneath a shell of ice, even tardigrades sealed away somewhere safe. But the sort of open surface conditions that complex Earth life leans on. The bare sky, the running streams, the green things turning sunlight into food are brutally hard to keep going on a planet struck by radiation of that intensity every few hours, without end. There is a second snag with these tight little temperate bands, and that is tidal locking. Because a red dwarf's band lies so near the star, the gravitational tug between the two over a geologically brief span is strong enough to fasten the planet's spin to its orbit. One face holds toward the star always, the other never sees it at all. A single hemisphere bakes in unending day beneath a red sun nailed motionless in the sky, while the far hemisphere lies in unending night, cold enough that even the gases of the air might freeze and fall as snow. The seam where the two meet, the terminator, is a thin belt of everlasting twilight, and that belt is the only ground where the temperature might suit standing water at all. A slender ring of possible life on a world that is otherwise either furnace or freezer. Some models propose that a thick enough atmosphere, stirring in the right patterns, could ferry heat from the scorched side to the frozen one, smoothing the extremes and widening the livable band. Other models propose the opposite, that the dayside air simply drifts to the night side and freezes out, leaving a planet with a frozen sea of nitrogen and oxygen across one half and no air whatsoever on the other. Which way it goes hangs on particulars we mostly do not yet know for any given world. The honest verdict is that a tidally locked planet in the temperate band might be livable in certain cases, along the strip, with the right air and the right fortune. Or it might be a cleaved world, half oven and half cold store, with only a narrow seam between where nothing is ever granted the time to take hold. So when we tot up temperate band worlds in the catalogs and reach a figure such as tens of billions spread through the galaxy, we owe it some honesty about what the figure contains. Most of those worlds circle red dwarfs. Most huddle nearer their star than Mercury huddles to ours. Most are taking flares many orders of magnitude beyond anything our sun throws, several times daily across the whole span of the star's existence. Many are tidally locked. The phrase temperate band, hung on worlds like these, is doing a great deal of work it has not really earned. The picture I keep returning to puts it as plainly as I can manage. A red dwarf's temperate band is like trying to keep a small campfire alive on a beach, while every few hours a wave the size of a house rolls straight over it, and goes on doing so for billions of years. Maybe a few embers are still glowing at the end of the night. Maybe. But the word livable is carrying a heavy load in that sentence, because whatever is still smoldering has spent its entire existence taking blows that would have snuffed out almost anything else. That is most of the lottery tickets in our hand. 3 of every 4. The bulk of the life candidates we are presently studying sit inside a brawl that never rings a final bell. There are exceptions. Some red dwarfs run calmer than the average, the older ones especially, whose magnetic temper has cooled over billions of years. And there are temperate band worlds around K-dwarfs and G-dwarfs, the orange and yellow stars, the sun being one of the latter, with the steady orange K-dwarfs often named the real sweet spot for life, calmer than red dwarfs and far longer lived than our own. But such stars are scarcer and harder to spot, and they are not where the bulk of today's observations happen to be aimed. The porch light still burns over TRAPPIST-1. It stutters half a dozen times a day, the bulbs unsteady, the wiring forever tripping. Each time you feel sure you are about to make out the house, the porch drops dark again, and then the surge returns, and the lamp flares so fiercely that for a moment you can see nothing else at all. That is what most of the lottery actually looks like. We have now toured a great many dead worlds. Worlds whose conditions packed up and left. Worlds whose star never once let them settle. Worlds caught in the wrong chapter of their sun's life. Worlds whose habitability rode a moving line that slid out past them.
It is worth halting here because so far we have been dwelling on deaths that belong to other worlds, other systems, distant suns.
The harder question is what our own planet's record really shows, because this world, the one we habitually cast as dependable and consistent, the planet that always came through, holds more endings inside it than most people suspect. The lights here came close to going out, again and again, and on one occasion they nearly went out because life itself had taught itself a brand new trick. The usual telling of Earth's story is that we drew a lucky hand. The sun is mild, the orbit holds firm, the moon steadied the tilt of our axis so the seasons never run amok, the magnetic field endures, the air endures, the water endures. We were given time, life turned up, life stayed, and here we are, swapping stories about how livable our world is, for the simple reason that we are here to swap them. In its broad shape, that telling is true. By every gauge we can bring to bear, Earth is an unusually steady world. 4 billion years through which conditions let life carry on, in one form or another, without ever resetting all the way to zero. That is no small thing. It may be the largest thing of all. But it is not the whole of it, because Earth has skated very near to going dark on more than one occasion. The rocks preserve evidence of 5 great mass extinctions, plus a long roster of lesser ones. Episodes in which so much of the planet's living variety was wiped out in a geologically brief flash that the fossil record itself thins to almost nothing. You can read the geological account of one of these in a single afternoon, though the recovery from it ran for millions of years. There simply is not much to set down. The fossils cease, the pollen ceases, the microfossils cease, the carbon ratios in the stone lurch, and the lights, briefly, blink out entirely. The 5 great ones are the Ordovician, Silurian, about 444 million years back, which erased some 85% of marine species. The late Devonian, near 372 million years back, which took out on the order of 3/4 of all species. The Permian, Triassic, dated near 252 million years back, the worst we have any record of. The Triassic, Jurassic, roughly 201 million years back, and the Cretaceous, Paleogene, of 66 million years back, the one with the 10-kilometer asteroid and the dinosaurs that nearly everyone meets in school. That Permian-Triassic event is the one most apt to leave anyone uneasy. It sometimes goes by the name the Great Dying, since the figures are so savage. Something like 96% of marine species were lost. Around 70% of land vertebrate species were lost. Even insects, famously near impossible to kill off, suffered in it the only mass extinction in their entire history. The fossils on the 2 sides of that line read like 2 unrelated planets. Almost nothing crossed over. The cause, by our best reading, was a colossal run of volcanic eruptions across what is today Siberia, an outpouring that buried something like 7 million square kilometers in lava and flushed staggering loads of carbon dioxide and sulfur compounds into the air, soured the seas, drained the oceans of their oxygen, and shoved the climate up by perhaps 10 degrees Celsius inside a brief geological window. The planet then needed somewhere between 5 and 10 million years to rebuild its ecological richness. Picture that. 5 to 10 million years in which life on Earth was, in any honest sense, on life support, clinging on, slowly piecing itself back together. That is the harshest one preserved in the fossil record. It is not, however, the harshest blow Earth has ever taken. The harshest came so deep in the past that it has scarcely left any fossil record behind. It fell upon single-celled creatures in shallow seas more than 2 billion years ahead of any of the extinctions whose names you might know. Its name is the Great Oxidation Event, and it is the eeriest disaster in the planet's whole biography, because no asteroid brought it, no volcano, no comet, no passing star.
life brought it on itself. Here is how it unfolded. For roughly the first 2 billion years that anything lived here, the ruling organisms were anaerobes. They drew their energy from chemistry that never touched oxygen, and there was no free oxygen in the air for them to touch.
Earth's early atmosphere was mostly nitrogen and carbon dioxide, laced with methane and water vapor and a scatter of other trace gases. Oxygen had no place on that list, because oxygen is ferociously reactive, forever latching onto other elements, and nothing was generating fresh, free oxygen in any real quantity. The bacteria and archaea of the young Earth ran on chemistries that would strike us as deeply alien now, feeding off hydrogen, off sulfur compounds, off iron compounds, off methane, living in deep-sea vents and shallow tide pools and layered columns of still water. They were the whole of the biosphere, and for some 2 billion years that was the entire face of life on this planet. The mats they built, the stromatolites, still grow today along shores such as Shark Bay in Western Australia, living postcards from that lost age. Then one particular lineage of bacteria, the forerunners of what we call cyanobacteria, stumbled onto a new trick. They worked out how to run photosynthesis using water as the source of electrons. Strip the jargon away and it comes to this. They learned to take sunlight, water, and carbon dioxide and assemble sugars, and the chemistry threw off a waste product, oxygen, raw O2 gas. The change crept in. Those first oxygen makers pushed their oxygen out into the water around them, where most of it was promptly devoured by reactions with the iron dissolved in the seawater and other hungry compounds. For a very long age, there was what geologists term an oxygen sink. The gas was being made, but the oceans drank it down nearly as fast as it appeared. The rocks still hold the receipts. The banded iron formations, those striped beds of rust red and dark gray you can still pick out across the outback of Western Australia and the Canadian North, are the fossil fingerprints of exactly that process. Alternating ribbons of iron oxide and silica laid down as the dissolved iron of the early seas rusted out of the water and settled, reacting with the climbing oxygen. Each ribbon is one chapter in the story of life, quietly fouling the chemistry of its own ocean. And those same beds are, by the way, where most of the iron the modern world mines actually comes from. In the end, the sinks filled. The dissolved iron had largely settled out. The oxygen now had nowhere left to flee but upward, and so it began to gather in the air. Atmospheric oxygen started its climb somewhere near 2.5 billion years in the past, and the moment it became truly significant, the Great Oxidation Event, as the geological marker, is dated to roughly 2.4 billion years in the past, by which point the levels had at last grown high enough to stamp a plain signature into the rock. For the overwhelming majority of living things back then, that was an apocalypse. To an organism that had evolved without it, oxygen is a venom. It is a reactive molecule that rips cellular chemistry to shreds. The anaerobic microbes that had built the entire living world across 2 billion years had no defense against it. They could digest a remarkable menu of strange chemicals, but oxygen was not on it. The rise of atmospheric oxygen, sluggish by the geological clock yet swift by the evolutionary one, snuffed out something like 80 to 99% of all life then alive. The exact figure resists pinning down, since the rocks at that depth preserve so little, but the genetic and chemical evidence all points to a calamity without precedent. The planet's first true mass extinction was not delivered by a stone from the sky. It was delivered by life, teaching itself to do a thing it had never managed before. That first great dying was, in the end, the very air we now have to breathe. And there is a cruel coda. By consuming the methane that had kept the young planet warm, that same oxygen helped tip Earth into the Huronian glaciation, one of the longest deep freezes it has ever known, a near-global sheet of ice on the heels of the suffocation. Let that one settle for a moment.
Every breath you have drawn today is part of the very atmosphere that 2.5 billion years in the past was a planetary catastrophe. The oxygen your brain depends on to form this thought is the same molecule that annihilated most of the biosphere the first time it built up to any real concentration. In its day, it was a poison. It turned into a fuel only later, once enough organisms had evolved the machinery to handle it.
The whole reason large, complex life is even possible is that oxygen is so rich in usable energy,
and animals like us carry metabolisms tuned to wring a great deal of it out. None of that arrives without that great oxygen catastrophe. And none of it arrives without life coming within a hair of killing itself off. The recovery dragged on for ages. Between that event and the first complex, many-celled creatures in the fossil record stretches a span of roughly 1 billion years so uneventful that paleontologists have nicknamed it the boring billion. Little stirs in the strata. Microbial life is present but hushed, catching its breath. The biosphere had been hit so brutally that it spent 1,000 million years simply putting itself back in order. In time, single cells learned to use oxygen efficiently. In time, eukaryotic cells appeared, with their inner organelles, built when one microbe swallowed another, and the two learned to live as one. In time, many-celled life arose. In time, animals walked on. But the gulf between the disaster and the recovery is staggering. The planet, in a genuine sense, nearly stopped breathing 5 separate times, and on one of those occasions the act of breathing was itself what nearly ended it. The air we now must have to live is the same air that, when it first arrived, was an extinction. That ought to reshape how you picture life on Earth. It has reshaped how I do. The image of Earth as a steady, life-cradling world is true, but only at the coarsest grain.
Yes, the planet has carried life without a break for close to 4 billion years. And yes, the conditions have stayed inside a band that life, in one guise or another, kept finding fresh corners to occupy. But inside that broad continuity sit at least 5 great resets, plus the largest reset of them all, the oxygen catastrophe. Nearly everything alive has perished, over and over, by different means for different reasons. Life's continuity on this planet is no thick braided rope. It is a run of slender single strands, some of which snapped, some of which held, the surviving strands carrying the whole of it onward each time. The bearing of all this on the question of life elsewhere is plain and bleak. If life on Earth, the very world we keep calling the success story, has come within a breath of erasure several times over, and once was nearly undone by its own waste gases, what are the chances that life on some other world has threaded the same needles and survived? What are the chances that a young planet somewhere evolved photosynthesis in some fashion, then choked to death on the oxygen it made and never came back? What are the chances some world suffered a furious volcanic age, or a great glaciation, or a shift in its air, and simply never recovered? We hold exactly one example of life that outlived its own evolution. That we are here at all proves it can be done. That it so nearly was not done, on the only example we possess, suggests it may fail far more often than it succeeds. That is a heavy thing to learn about your own planet. Earth came close to falling silent.
In places, the fossil record thins out enough to read in one afternoon. The whole, all of which, opens a different question. So far, we have been asking what becomes of life once it is already underway. We have not yet asked how often life manages to get underway in the first place, and that, it turns out, is a question we cannot answer well either. We hold exactly one instance, and a single instance tells you next to nothing about how common the thing really is. There is a habit, when the talk turns to habitable planets, of treating habitable and inhabited as though they were one word. They are not. The two are not even close. Habitability describes a set of conditions. Inhabitation describes what is actually alive in a place. The first is a sort of curriculum vitae. The second is whether anyone ever turned up to take the post. Here is what we genuinely know about life beginning on a world. We know it can occur because we stand on a world where it did. That is one measurement. That is the whole of the data set. We do not know how reliably it occurs where the conditions permit. We do not know whether, given enough time, it always lights. We do not know whether it usually fizzles. We do not even know how, peering in from outside a planet, to judge whether life ever stirred there at all. We have hints. We do not have answers.
What we do have is this. Earth carried liquid water on its surface for somewhere between 100 million and 700 million years before any unambiguous sign of life appears in the rock. That is the interval between a world being livable and a world being lived in, measured on the one planet we know to be both. Estimates of when Earth's seas first held steady as liquid water reach from around 4.4 billion years ago, drawn from the ancient zircon crystals of the Jack Hills in Australia, down to roughly 4 billion, depending on the model you favor. Estimates of the earliest persuasive trace of biology, the graphite specks of Greenland's Isua rocks, the stromatolite mats of the Pilbara, stretch from roughly 4 billion years in the past, inward to something nearer 3.5 billion. So the lag between Earth being able to host life and Earth actually wearing it falls somewhere between nothing at all and 700 million years. That lag matters because we cannot see what filled it. Did life ignite almost the instant conditions allowed, the apparent delay just a trick of a patchy rock record? Or did chemistry have to run and rerun for 500 million years before the first self-sustaining system finally caught? The answer to that one question would settle more than nearly any other single fact, whether life runs widespread through the universe or stays staggeringly rare. The maddening truth is that we cannot say. The oldest fossils are contested. The oldest chemical fingerprints, the lopsided carbon isotope ratios that living metabolism tends to leave, are contested. The oldest microbial mats are contested. The oldest direct sign of cells is contested. Researchers publish papers nudging these dates in both directions every year, and the field refuses to settle. The honest summary is that life on Earth began somewhere between very fast and very slow, and we cannot say which. What we are able to do is weigh how steep that first step really is. The passage from lifeless chemistry to a self-feeding, self-copying, evolving cell is a problem hard even to define, let alone crack. It demands a very particular sort of chemistry. You need a way to store information, something like DNA or RNA, which is why many origin researchers suspect a vanished RNA world came first. You need a way to turn that information into action, proteins or something playing their part. Then a way to wall the system off, a membrane. You need a source of energy, perhaps the kind welling up at deep-sea hydrothermal vents, the warm mineral chimneys of fields like the one named Lost City. And you need a way of copying that is sloppy enough for variation to gather, yet faithful enough that the whole thing does not dissolve into noise. All of those have to come together, in some form, on a world that grants them time to assemble into the single ancestor every living thing descends from. None of that is trivial. The famous Miller-Urey experiment of 1952 showed that sparks through the right gases will readily build amino acids, the beads of the chain, but a heap of beads is a long way from a living, threading needle. There are biochemists who judge the assembly of that first cell so improbable it might happen just once in the whole lifetime of a galaxy by blind luck. There are biochemists who judge it so favorable it ought to occur on any suitably stocked world within a scant few million years. Both camps are clever. Both camps are reading the same evidence. They split apart because the problem is truly hard and the evidence truly thin.
A useful way to hold this is to picture the gap between casting a seed onto bare rock and tucking one into rich earth. Cast a seed onto bare rock and you can be fairly certain nothing follows. The conditions are wrong. The seed simply lies there. That is most of what fills the exoplanet catalog, soil that was never going to take. But here is the part that needs a moment to land. Pressing a seed into rich earth still guarantees you nothing. Sometimes a sapling rises. Sometimes the ground stays bare. The seed may be the wrong sort for that earth, or too old to stir, or snatched by a bird before it ever cracks open. The earth may pass every test you ran and still be quietly off in some way you never thought to measure. Rich ground is required, yet on its own it is not enough. The seed itself must catch. Soil is what habitability amounts to. Whether anything ever truly grew from that soil is a wholly separate matter, and not one we can answer in any general way. Out there, the cosmos is casting seeds onto hundreds of billions of worlds. We have no idea what share of them sprout. We have one tree in view, and no way to know whether the field around it is crowded with other trees we simply cannot make out, or whether it is mostly bare ground with this one lone tree rooted in it. Of all of them, Mars is the most painful to dwell on, because it sat there holding all it required for a long stretch, and we still cannot tell. Across many hundreds of millions of years, this world kept standing water. It wore an atmosphere. It ran a magnetic field for a spell. It had the right chemistry and energy to burn in its volcanoes and its buried hydrothermal plumbing. By every yardstick we can apply across the distance, Mars was a world that should have been capable of carrying life in the very same age when life was finding its feet here on Earth. Did it? We do not know. We possess a sealed tube. Inside it sits a stone marked with patterns that, on Earth, a textbook would read as the fingerprint of microbes. We have the cautious wording of the team that published the work, the wording of suspicion rather than proof. We have, as these words are recorded, no means of bringing that tube home, and the timetable for fetching it has slipped out toward the late 2030s, perhaps beyond. And should we ever retrieve it? Should it come home? Should the laboratory confirm past reasonable doubt that the rock holds traces of biology from 3.5 billion years back, that would hand us a second instance, 2 worlds within a single solar system where life arose. From 2 instances, we still could not state how frequently life appears across the universe at large. We would hold a far better estimate. We would have achieved one of the most momentous discoveries our species has ever made. But we would still be reasoning from one solar system alone. Venus is worse still. It may have kept liquid oceans for 2 or 3 billion years, and we can never truly check whether anything ever swam in them. Present-day Venus, all acid cloud and lead-softening heat and crushing weight of air, has preserved no biological record from its livable youth. Whatever fossils it might once have held have been baked, crushed, and scrubbed out of the crust by chemistry. The boldest mission concepts for Venus send probes to drift through the upper cloud decks, where temperature and pressure ease toward something almost Earth-like, and the Da Vinci probe will soon fall the whole way down through that air. There is even live argument, ever since a contested whiff of phosphine was reported in 2020, about whether microbes might persist in the cloud layer right now, in a temperate band some 50 kilometers above the ground. But those are searches for the present. Its deep past is gone beyond recovery, which leaves the other worlds we have not even mentioned yet. Europa, the icy moon of Jupiter, hiding a whole ocean of liquid water under a frozen rind perhaps 20 kilometers deep, with the Europa Clipper spacecraft, launched in the autumn of 2024, already crossing the dark toward it. Enceladus, a small moon of Saturn, jetting fountains of water vapor into space through fissures in its frozen skin, a sign of a sea sloshing beneath, the very plumes through which the Cassini probe once flew and tasted, finding organic molecules and hydrogen in the spray. Titan, the largest of Saturn's moons, wrapped in a thick orange atmosphere with lakes of liquid methane lying on its surface, and the faint possibility of a chemistry so unfamiliar it might amount to a separate kind of life altogether. A world the Dragonfly rotorcraft is being built to go and explore. There are corners of our own planetary system where conditions for some manner of biology genuinely exist, and we have scarcely started to look. Beyond all that lie the exoplanets, some 6,000 now confirmed and hundreds of billions more inferred. Even with the boldest telescopes we could ever dream of raising, we will almost surely never lay hands on one. What we can do is gather the light from such a world after its long crossing of the light years and read the chemistry of its air. We can search it for water vapor. We can search for oxygen, which on any rocky world whispers of photosynthesis. We can search for methane. We can search for mixtures of gases that ought never to coexist in balance, a tell that something is steadily topping them up. That is the kit we hold. It is a formidable kit, but it is a kit for reading fingerprints left in air. It is not a kit for lowering a tube to the ground and hauling it back. So even armed with the finest instruments we will ever possess, we may flag candidate biosignatures on dozens of distant worlds across the coming decades. And we will most likely never get to confirm a single one by going. We will be exactly where we stand with Mars, only multiplied by hundreds. A rock beyond our reach, a signal we cannot chase down, a maybe we can never close. Here is a thought experiment I find clarifying. Picture an alien astronomer, somewhere out in the dark, observing our solar system from a couple of hundred light years off. Their telescopes are superb. They pick out the orbital tug of all 8 planets. They read the atmospheres of the rocky few. They turn to Earth and find oxygen, water vapor, methane, ozone, a suite of markers that, by their finest models, reads like a living world. They write it up. They publish the result. They add Earth to their roster of candidates. What they cannot do is travel here. They cannot dispatch a probe. They cannot carry home a sample. The gulf is simply too wide. They will know Earth most likely holds life. The form that life takes, they will never make out. Confirmation will forever stay beyond them. They will pass the whole remaining span of their civilization with Earth as a mark on a chart, a line on a roster of maybes, a possibility they cannot bring to a close. That is exactly our situation with the 6,000, with the 60,000 to come, with the hundreds of billions past them. We will build a catalog. It will be partial. A few of its entries will prove correct, others will prove false alarms, and only seldom will we be handed the chance to find out which. As for the Mars tube, drilled in mid-2024 and perhaps not recovered before the late 2030s, it is as close as we will ever get to a real sample. That is the one we have. A single tube, out of reach, with every rival world lying very much farther still, which leaves it the high point of the whole enterprise, the most consequential stone we possess, sitting out on another planet inside a sealed cylinder in the wind. And whether we manage to carry it back before its drillers have all retired is genuinely uncertain. All of this means that the moment we look upward and try to reckon who is and is not out there, we must stay careful about what we are genuinely looking at. Because what arrives down here is no frozen snapshot of the cosmos as it stands tonight. It is something stranger. And once you notice the difference, you cannot stop noticing it. Step outside on a night dark enough to really show the stars, and what lies above you is not the sky. It is a record. Every spark you can pick out, by naked eye or binoculars or telescope, is a beam that has been racing toward you for some length of time before it struck your eye. The sun overhead is 8 minutes and 20 seconds old. the Moon, a touch over a single second. Sirius, brightest of the night stars, sits roughly 8.6 light-years out, so the beam reaching your eye left it the better part of a decade back, around the time of some half-remembered moment in your own life. Whatever Sirius is doing at this very second will not get here for another 8.6 years yet. Light is quick. Set against the galaxy, it is achingly slow. Proxima Centauri, the Sun's closest neighbor, lies 4.24 light-years away, and the glow you catch from it set out 4 years and change ago. Polaris, the pole star, stands roughly 430 light-years off. The light from it you see tonight departed while Galileo still drew breath, perhaps earlier. The brightest stars you can see unaided mostly lie within a couple hundred light-years of us. The dimmest naked-eye ones reach out to several thousand. And a few of the points a pair of binoculars reveals are so remote their light has flown for tens of thousands of years to reach you. The glow at the heart of the Milky Way, that faint smudge along a dark sky, left the galactic core some 26,000 years back. The light of the Andromeda Galaxy. The one other great galaxy you can usually catch without a telescope, has been on the road for roughly 2.5 million years. The Andromeda light entering your eye tonight set out before our ancestors had farmed a field or spoken a language we would know as one. Andromeda's light is older than our whole species. Then come the galaxies that the James Webb Telescope keeps turning up at the rim of the observable universe. The farthest it has imaged flung their light outward when the cosmos had lived through less than 5% of its present age, light that has been traveling more than 13 billion years to find us. The galaxy responsible has shifted past anything we could measure. It may yet survive in some form, it may not. Whatever it looks like now, we have no means of seeing that current version. We see only its version from 13 billion years in the past. So as you tip your head back to the sky, you are, quite literally, gazing into the deep past. That this is technically so is a line everyone hears at some point in school. What it actually means to live inside a universe built this way is far harder to take in. What it really amounts to is this: the night sky works like a postal service. Every single point of light is a piece of mail, and each piece was posted at a wildly different moment. They all land in your eye together this instant, though not one of them was sent at the same time as another. Some were posted yesterday, some 1,000 years ago, some during the Roman Empire, some long before any ancestor of ours first stood upright. And a few were posted by senders who, by the hour the letter arrived, had already ceased to exist. That last part is the one that needs a minute to sink in. Stars die, rarely on a human clock, but ceaselessly on a galactic one. There are stars hanging in the night that, sometime in the last few centuries or millennia, have already ended, spent their fuel, collapsed, shrugged off their outer shells, and settled into being white dwarfs, neutron stars, or black holes. Betelgeuse, the red shoulder of Orion, is the famous candidate. So far gone it may already have detonated while its last calm light is still en route. The change may be gradual, a small star subsiding into a cinder, or abrupt, a supernova blast. Whichever the case, the star in your eye is not the star that stands there now. What hangs there is only a memory, its light still crossing, still bound to cross for years or centuries or whole millennia after the star itself has died. Somewhere in the sky above you, at this very moment, the light of at least one star is still landing in your eye, even though the body that cast it no longer exists in any shape we would know. You cannot pick out which one. The envelope gives nothing away. The letter looks identical to those mailed by senders very much still alive. You only know, as a certainty, that a few of them come from senders who are not. In a genuine sense, the sky we look at is a memorial. Let me press that thought further, because it joins up with everything we have turned over tonight. Every livable planet we have already found, or might find in the decades ahead, is likewise a letter out of the past. The glow from a world circling a star 50 light-years off is half a century old by the time it lands here, which means the air we measure on it is half a century stale. Push the star out to 100 light-years, and the reading is a century behind. Push it to 1,000, and the reading trails by 10 centuries. For a planet, that hardly seems to matter. The makeup of an atmosphere usually shifts at a crawl, and a few stray centuries on a world billions of years old ought to count for little, and mostly it does. But out at the very edge of what we could ever hope to detect, or the instant we begin asking whether one particular planet is inhabited right now, the lag turns decisive. Light from a world 10,000 light-years away shows us the air at war 100 centuries ago. Whole civilizations can rise and fall inside that gap. Suppose a technological people lived on such a world, lasted some 5,000 years, and then fell. And suppose their fall came 9,000 years before the light we are presently catching set out. Then we might be staring at the glow of a culture still in full swing. Had their collapse come 11,000 years ago instead, we would be reading light sent after they had vanished, and we would find no trace of them at all. Whether, at this instant, anyone is out there is simply not a question we can answer head-on. We can only ask whether someone happened to be there in the moment the light departed. We cannot ask about now at all. The very idea of now, stretched across a star system that lies thousands of light-years off, carries no meaning we can put to any test. This is the relativity of simultaneity that Einstein worked out, the plain fact that now is a purely local affair. The universe keeps no single, shared present. So when we gaze upward and try to work out who is and is not out there, we are, in effect, prying open a postbox crammed with letters of every age, from every sort of sender, stamped with dates we cannot wholly trust. A few arrive from people still at their address, a few from people long since moved away, a few from people who died well before the envelope landed. We sift the pile, we do our best, we draw our charts. Those charts are genuinely useful, and they are also at bottom charts of a place that might no longer exist in the shape they record. Which brings us to the harder thing we have been circling all night. The universe may not be empty. It may be a graveyard. A vast share of the lights overhead might be streaming from places where life flared and then went out, long before that light ever set off toward you. The deaths could lie so deep in the past that the news of them has not yet crossed the gap. The news is in transit. It is 50 light-years out, or 100, or 1,000, moving at the one speed that information is allowed to move through this universe, a touch under 300,000 kilometers every second. We will receive the news. We just cannot know when. We will spot a star and weigh its planet and turn up a signature that wears the look of life, and that fingerprint may belong to a world that lost its life ages before the moment of our reading, and we will have no way to tell. The honest form of stargazing, the kind that takes the physics at its word, is that we are sorting mail. Some of it is fresh, some of it is ancient. Some senders are still at their address, some no longer are. The postbox is beyond enormous, the letters never stop coming, and you could sort for a lifetime and never reach the bottom. A particular feeling arrives with this, late in the night, when you truly let it land. You head outside, you tilt your gaze upward, and you settle your eye on one bright star, and you hold it there a moment, and you think about the long years that light has been crossing the dark. You think of what was unfolding on Earth the day that light first set out. You think of what was unfolding on whatever world dispatched it, if a world was even there, if anyone was, and what they might have been about on the day that one particle of light left them for its enormous journey. And then it strikes you that this is a single particle out of the trillions hitting your eye each second, that every star is forever posting letters, that the postbox is filled past any hope of comprehension, and that one upward glance takes in more mail than a person could ever read. Some of it comes from senders still living. Some of it does not. You cannot tell which from down here. Not yet. And it is worth remembering that we have posted a letter of our own into that same dark. The golden records riding the 2 Voyager craft, our return address fixed to a bottle thrown on the cosmic tide. Which leaves one last thing to speak of, the single patch of sky we can genuinely act upon, the one beneath our feet. There is an instinct, whenever this subject surfaces, to frame our planet as the great exception, the one that worked. Lucky in its planet, lucky in its orbit, lucky in its steady star, blessed with the right moon and a lasting magnetic field and a breathable sky and a biology that took every break landing in our favor, everything somehow holding, so that here we sit 4 billion years deep into the tail, drawing breath from the very air that nearly wrecked the living world when it first arrived, looking up at worlds that did not survive, and feeling, somewhere beneath the ribs, that we belong to a different roster than they do. We belong to precisely the same roster. Our planet is no exception. It is the one caught mid-story. It is at the stretch of the tail where the lamps are still lit, but the clock has begun to tick. That we are here in this particular instant is not because our world is built differently from Mars or Venus. It is because we arrived at the right hour. We sit inside an open window. That window will close. Let me set the numbers out, because they are not vague, they are exact. Earth came together around 4.5 billion years back. Surface water reaches at least 4 billion years deep, perhaps as far as 4.4. Life leaves its mark in the rock somewhere in the range of 3.5 to 4 billion years ago. Complex, many-celled life turns up near 600 million years back, hard-shelled animals near 540 million, the first land plants near 470 million. The dinosaurs span the stretch from roughly 230 down to 66 million. Our own kind, near 300,000 years ago. The turn to farming, some 12,000 years back. Industrial civilization, a mere 2 centuries. That is the road behind us. Now, turn and face forward. The sun, as we noted earlier, has been brightening by something close to 1/10 every billion years, and the brightening does not stop. Several independent lines of evidence and modeling settle on a window of roughly 1 to 1.5 billion years from here, before conditions on Earth grow too hot for complex, many-celled life to keep working. That does not mean the planet turns lethal overnight. It means the slow grind of warming, evaporation, air loss, and falling oxygen finally crosses a line past which the kinds of ecosystems we know cannot carry on. The seas will be steaming away. The plants that need steady temperatures will falter. The food webs resting on those plants will falter, and the creatures at the top of those webs, any version of us among them, will be in deep trouble. Microbes may cling on beyond that line. Even today, certain organisms on this planet thrive in conditions that would snuff out nearly everything else. They dwell in deep rock, in scalding water, in the chemistry of aquifers far below ground, in harsh pockets where what happens at the surface stopped mattering a very long time ago. Some of that life could persist for many hundreds of millions of years beyond the point when the surface turns lethal to everything else. Earth's biological story may well close with the same sort of creatures it opened with, microbes in the dark, carrying quietly on, in places that no longer keep a sky overhead worth lifting your eyes to. That is only the first act of the ending. Somewhere within the next 1 to 1.5 billion years, the surface ceases to be a home for complex life. The biosphere caves in, the air begins to shift, the seas start to drain away. The very processes that ran their course on Venus begin, on another clock and by another route, to run here. By something like 3 or 4 billion years out, Earth's surface runs hot enough that the seas have all but boiled off. The atmosphere is thinning, carbon dioxide is mounting, and the planet is turning, in slow motion, into a hotter, drier, far less forgiving version of the world it once was. The restless engine of plate tectonics runs on water, in the crust and on the surface alike, regulated by a slow carbonate silicate thermostat, and as the water departs, that engine begins to seize. Earth by then would resemble the Earth we know in almost nothing. The continents would remain, the mountains would remain, the oceans would not. Roughly 5 billion years hence, the sun will burn through the hydrogen in its core, ending a main sequence life of about 10 billion years, and swell into a red giant. Its outer envelope balloons outward. Mercury is consumed. Venus is consumed. By the most recent modeling, a run of papers from the past few years that refine the sum by folding in the sun's loss of mass and the drag of tides, the central estimate has the Earth ending up inside the bloated star as well. A few studies allow that Earth's orbit might creep outward far enough to slip clear of the swelling envelope, leaving a charred, airless stone circling a slowly cooling giant. Others find that drag from that swollen outer atmosphere hauls the planet inward and swallows it. By the central estimate, for whatever it is worth, Earth does not survive. The likeliest date for that engulfment lands near 7.5 billion years from now. That is the figure most often quoted. The real physics carries more uncertainty than a single number admits, but 7.5 billion is the working answer. So here is the entire window laid out. This world has already been livable for some 4 billion years, and it will hold its livability for perhaps another billion to 1.5 billion on top of that, which puts the planet's whole habitable lifetime, first breath to last, in the neighborhood of 5-odd billion years all told. We are, plainly, past the midpoint. Let me put it once more, because this is the part that is difficult to hear and simple to slide past. Of a habitable run lasting something over 5 billion years, we are already roughly 4 billion years deep, with maybe 1 billion or 1.5 billion still to come. The greater share of Earth's life-bearing history lies behind us now, not ahead. That is no doomsday cry. It is not next week. It falls in no time frame that ought to touch a single choice any living person makes about anything in an actual life. 1 billion years ahead is so remote, the continents themselves will by then have drifted and fused into shapes nobody now alive would know. A future supercontinent geologists already sketch and call Pangaea Ultima. Whatever lives on Earth 1 billion years out will differ from us as sharply as we differ from those earliest eukaryotic cells. Our species itself will be gone. The civilization we have built will be gone. The languages we speak will be gone. And the Earth itself will only faintly echo the world we know today. But the planet's own arc, the long curve of the world as a world, has passed its middle. This world is well past its morning. It stands well into its late afternoon, with evening not yet begun, though in time it surely will. The window stands open for now. It will not stay open forever. That is the third unsettling truth I meant to leave you holding, and not because it terrifies. It is simply true. Across its own long arc, Earth is no exception. It is rather the one now showing what a livable world looks like in the chapter of the story where it is actually underway. Mars showed us what comes afterward. Venus showed us what comes afterward by a different road. Earth is letting us watch the during as it happens, and that middle stretch is the entire point. It is the during that lends the universe any interest at all in the moments it occurs, and the during, by our best reckoning, is rare, in space and in time alike. In the deep future, Earth's air will climb through its own runaway and finally bleed off. The mechanism differs from the Martian one, but the ending rhymes all the same. As the sun brightens, the high air warms. Water vapor rides up far enough for ultraviolet light to tear it apart. The hydrogen flees to space. The oxygen is locked into stone or burned away. The pressure falls, and the magnetic field, depending on how the planet's interior ages, may or may not fade alongside it. The end state of Earth, 3 or 4 billion years on, looks like a milder Mars or a milder Venus, whichever physics prevails. Either way, the destination is much the same: a dead world under a thin or vanished atmosphere, with no liquid water on its face and no biosphere, circling a star itself, drawing toward the close of its main sequence life, and bound, in the end, to shrink into a white dwarf. Recall how Mars lost its air. The shield fell, the wind plucked at the atmosphere, the pressure sank away across long hundreds of millions of years. And Mars, in a very real way, is what Earth is slowly in the act of becoming, merely on another schedule. Mars was the dead stranger when this began. Mars is, just as much, the preview of it. The way I have come to hold the whole of it is as a single, long evening. The day is done, the evening come, the light still warm, the window still standing open. Night is on its way, yet night has not arrived. We are allowed to sit out on this planet's porch for as long as it remains possible to sit out on this planet's porch at all, and gaze up at the sky, and sort through the letters, and wonder who else, somewhere in the dark, might likewise be out on a porch of their own, while their own light still holds warm. That window will not stay open, that is true. It is equally true that right now the window stands open. Both hold at once. The thing about an open window is that all that finally matters is whether it stands open in the moment you happen to be standing in. Earth's window stands open. Its oceans remain liquid. Its air remains fit to breathe. Its magnetic field remains in place, and the planet goes on doing the work that a life-bearing world has to do. Not one piece of that has broken. If I had to fix on a single image for this, it would be the feeling of a certain kind of evening, the kind where the air has finally cooled after a scorching day, where the light is turning gold, where you know full well the dark is coming, and yet it has not come, where you can sit outdoors and feel neither cold nor hot, while the world carries on with its small, ordinary business all around you. An evening like that does not last. It cannot. Nightfall is coming. But nightfall has not arrived. And that is exactly the moment we are living in. Our planet is living through one of those evenings, an evening several 100 million years in length, and we are handed only the thinnest sliver of it to inhabit. It is good, and it is warm, and it is going to end, and not one of those three facts cancels either of the others. There is something genuinely strange in being the one species that worked out the timetable. Not one of the other creatures sharing this planet has any inkling that any of it is underway. The dolphins do not know. The crows do not know. The trees do not know. Only we have run the arithmetic. Only we have read the rock and the stellar physics and pinned down, with real precision, the whereabouts we occupy along the long sweep of our own arc. That understanding is genuinely new. With anything approaching the precision we now command, people have held it for only a few decades, and its weight has barely started to seep into the wider culture. The great majority still picture our planet as the fixed and permanent thing in the room, which is why your carrying it matters at all. Because the moment you take it in, three things quietly change together. The sky overhead reads differently. The lamp on the porch reads differently. And the old question of whether we share the dark with anyone at all reads differently too, turning from a tally of how many neighbors we might have into something stranger. Which of them still keep a light burning? Which once did and no longer do? Which never managed to at all? And which might, at this very instant, be bent over their own edition of this same sky, looking back our way and turning the identical thoughts. For now, the lamp is still lit on our own porch. Let me stay a while longer in the place we have reached, because its texture is the whole point of the exercise. What this conversation has really been about is not the facts, but the shift they produce in the way you read the sky. The facts are scaffolding, and the shift is the building that goes up behind them.
Take in that habitable windows mostly swing shut, that mild stars are the exception rather than the rule, that planets resembling ours are vanishingly few, and that even ours has slipped beyond the midpoint of its own arc, and the sky stops posing the question of who is out there and starts posing the question of when. On each of those distant worlds, you find yourself wondering at what hour the conditions arrived, at what hour they slipped away, whether anything ever rose to make use of the interval, and whether any of them might be running, right now, the very experiment Earth is running, somewhere deep in their own long evening, peering back through the dark toward glimmers that might or might not still shelter a tenant. It is a wholly different way to hold the sky, less a search for company than a survey of overlapping times, a few of which coincide with ours while most slide past in the dark. Seen this way, the galaxy is no city of neighbors, but something nearer an archive of moments. Every star and every planet a separate slice of time bearing its own opening and span and close. And those slices almost never line up. The place teems with lives that started and finished long before us, and others that will not begin until we are gone. We move through that archive mostly blind, catching only those slices whose light is arriving just now, and able to act on only the few we can actually study. And far from bleak. That turns out to be clarifying once you sit with it, because the worn old choice we are handed, that we are either alone or surrounded, is a two-sided coin that simply does not fit the cosmos we live in. The reality is that we occupy one moment among many that have already gone, and many still to come. And the matter of company is not really one of presence or absence in any flat absolute sense at all. It is a matter of overlap. Overlap is precisely the quantity we have never built a decent instrument to read. Across the gulf of light years, time is far harder to pin down than mere distance. A star's spectrum hands you its composition and its temperature. A planet's transit hands you its size and how tightly it orbits. The spectrum of an atmosphere, when we can capture it, hands you the makeup of the air. What none of those readings ever hands you is the where in its own history of the snapshot. You are always staring at a single frozen instant, and always blind to the timeline around it. This is, when you trace it down, the great buried unknown of the famous Drake equation, the term written as L, the sheer longevity of a living or broadcasting world, the one factor the whole estimate leans on hardest, and the one we can least constrain. It is the quiet engine of the Fermi paradox, too, the riddle of why a galaxy this ancient and this vast should sit so silent. So the matter of whether the cosmos stands empty turns out to carry a soft, double-edged answer we rarely dwell on. Empty as far as the present goes, perhaps. Brimming if you weigh all of time at once, also perhaps. Both can be true in the same breath, the difference resting entirely on when the snapshot is taken. And the only snapshot we are permitted is the one our position and our instruments allow, here in our own thin sliver of time. What I keep returning to in the small hours is this: the likelihood that there have been worlds where life arrived, persisted for a stretch, and then ended, ranks among the most quietly staggering things our species has ever worked out. As a sentence put rigorously, it could not honestly be spoken until the last few decades. Before that, you could speculate, spin fiction, dream, but you could not argue it from the physics. And now you can. The physics does not quite force the conclusion.
yet it now supports it firmly enough to build a coherent picture on. And the picture is simply this: worlds happen, and then they stop happening. The cosmos is in the trade of raising places where the lights kindle, hold for a time, then fail. Among the bare handful we have managed to draw close enough to examine, some may once have held life, some may have held nothing, and some may be holding something even now, in their own local present, that will stay hidden from us for 1,000,000 years because its light has not yet finished crossing to us. That is the universe. That is what is actually out there. Neither a void nor a crowd, but an archive of long evenings, each frozen at a different stage of the one long story, with our own evening playing out right here.
And there is a last thing I want to set down, because it has shadowed this whole conversation and rarely makes it into the science at all. The fact that our planet has passed its middle takes nothing away from how fine this evening still is. The air still holds its warmth, a lamp still burns in the kitchen window, and the voices inside have not fallen silent. Seasons keep turning, rain keeps falling, stars keep rising after dusk. Whatever is on its way is on its way, and it is not tonight. Tonight is simply one of the nights that fall inside the open window. If you have stayed with me this far, a particular quiet may have begun to settle over you, and it is neither pessimism nor optimism, but a third thing entirely. The thing that arrives when you let the true scale of it land without forcing it into something cozier or grimmer than it is. The cosmos has been underway for 13.8 billion years, our planet for about 4.5, life upon it for roughly 4, our own kind for some 300,000, settled civilization for a mere 10. We are a sliver tucked inside a sliver. What came before us is gone. What comes after is not yet here. And the only sliver we will ever feel from the inside is this one, which happens to be warm, right now, tonight. That is as close as I can get to what all of this is truly about. Not fear, not awe, just a clear-eyed noticing of where you happen to stand. In this moment, our planet is doing the one thing a world only manages across the thinnest slice of its lifetime. It is carrying life.
It runs the weather, keeps an atmosphere wrapped around itself, holds its water as liquid, spins at a steady clip, shields itself behind a magnetic field that still holds, and grants us the sort of night in which you can walk out under the stars and neither freeze nor cook nor choke. That is the gift, the single gift the cosmos ever made us, and everything else we have is downstream of it. Mars once had something close. Venus kept it for longer. Each of them lost it, by a different mechanism but to the same end. The window closed, and the lights within went dark. Their porch lamps still shine in the narrow sense that sunlight still falls on them, but nothing else is lit, and the houses stand empty. We have been rapping on the door of Mars for 60 years now. We have scarcely raised a hand toward Venus, and most of the other worlds we will surely never knock on at all. The distance is too vast, the journeys too long, the instruments still half built. But there is one knock we can make out right now, the most useful one of all, and it has nothing whatever to do with other worlds. It comes from this one: the wind outside, the shifting trees, the patter of rain on the roof, if you live where it rains, the breath of whoever lies beside you, if anyone does, a refrigerator's hum, the far-off murmur of a road, the small tick of a clock. Whatever is making any sound at all in your room tonight is a planet that is still alive, speaking aloud, a sound that has run unbroken, in one form or another, for 4 billion years. That sound is the gift. That sound is the whole of what we mean by the word habitable. And that sound, in the long reach of things, will one day cease. Not for you, nor for anyone you will ever meet, nor for any addition of any civilization any human being will ever raise. But across the long arc, it will stop. The planet will fall silent. The wind will go on blowing a while afterward, only it will be stirring a different air over a different world that merely keeps the old name. The thread that runs on, then, will not be a living one. It will be the slow, geological kind. The rocks will hold some memory of us, in fossils that might or might not ever be read by anyone or anything, and we will settle into being a single layer in somebody else's deep history. All of that, though, lies far off. None of it is now. Now the lamp on the porch still burns. Now the kitchen is still warm. Now the window is open. That is where I want to leave the long stretch of tonight, with the window still open, the porch lamp lit, the gift still running. There is one last thing to say, and then we are done. Having come this far with me, you have heard about Mars, about Venus, about worlds we will almost certainly never set foot upon. You have heard about life nearly ending itself by learning to breathe. You have heard the strange, hushed fact that Earth itself, the warmest house on the street, keeps its porch lamp wired to a timer. What I want to leave you holding is not a fact at all. When we tip our heads back, we are inclined to imagine the cosmos as one of two things: packed with company or utterly deserted, a crowd or a vacancy. But a third shape exists, and it may be the truest of the three. The cosmos might be neither of those. It might instead be somewhere that life flares up and then does not, where worlds are handed their billion good years and afterward go still, where the porch lamps burn on long after everyone indoors has gone. That does not make us any less rare. If anything, it sharpens our rarity, not because nothing else ever managed it, but because something else, somewhere, once did, and then stopped, while we are somehow still here for the time being. Earth's window stands open. It will not stand open forever, but it stands open tonight. The seas still run liquid. The air still serves the lungs. The magnetic shield still stands raised. The slow geological clock that holds the carbon cycle in balance is still ticking. The living things are still adapting, and the seasons are still wheeling round. That rare act a planet manages only for a sliver of its days, the act we call carrying life, is one this world is performing at this very minute, and you are a piece of the proof. You are reading or hearing or half dreaming these words, sliding towards sleep with them murmuring in the background, only because Earth is, just now, permitting it all. Somewhere on a world we have not yet found, those same conditions might hold true tonight, and someone upon it might be turning their face to a sky that has our own sun somewhere in it, wondering the very thing you are wondering. Perhaps they are framing it in a tongue with not one sound in common with ours. Perhaps they are using no words whatever. Perhaps they merely carry an inward sense, in whatever stands in for awareness in them, that the night is enormous, and they are a small thing inside it, and something, somewhere, might be looking back. Or perhaps not. Perhaps their lamps went dark a very long while ago, and the news has not reached us. Perhaps the light we would need in order to see them at all, to prove they were ever real, is still somewhere out on the road, taking its centuries or its thousands of years to arrive. Perhaps by the time the message lands, the senders will be gone, and we will be left to work out, from the message itself, what they ever meant by it. Or perhaps no one is out there in the slightest, and the cosmos is as empty as the loudest form of the loneliness case insists. Perhaps Earth truly is the one spot where the chemistry ever fell into place. Perhaps we are, quite literally, the single living thing in this entire galaxy, or in any galaxy we will ever lay eyes on. That last possibility is one you are allowed to sit with too. It need not be the likeliest answer. It only needs to be permitted. The plain fact that we do not know
is the actual situation we are in, and not knowing is no problem to be solved before the night is out. It is a place to sit for the time being, until more comes in, and some of it will, and some of it never will. The cosmos is patient. The cosmos is also old enough to afford its patience. We have far less time than it does, yet we have enough to see us through tonight. Either way, the porch lamp is still burning here, the sky is still wheeling overhead, the numbers still hold, the water still runs liquid, the lungs still pull in breath, and the rock beneath your feet is old enough to recall things you could never picture, and steady enough to keep up its slow work of holding the world together for a further billion years yet, give or take. Mars keeps its porch lamp lit, in the dry, technical sense that sunlight still touches it, though the house behind the door is empty. Venus keeps hers lit too, in her own fashion, behind veils of sulfuric cloud, on a planet glowing hot beneath a heavy, dim-lit sky. TRAPPIST-1 goes on flaring half a dozen times a day. The library still stands, its lamps mostly dark and its shelves still crowded. The postbox is still taking deliveries. And here, tonight, you find yourself inside a moment that the vast majority of planets are never granted at all. You do not have to do a single thing with that. You do not have to summon awe or sorrow or any feeling in particular. You can simply take note of it. The window stands open. You are in the room. The warmth is real, and the night will close the way nights always do. Morning, should there be a morning where you happen to be, will arrive in its own time. The seasons will go on turning. The earth will go on doing what it has done across 4 billion years, for just as long as it possibly can. The lamps are still lit here, for the present. And if I had to hand you one thing to carry away from all of it, it would not be a fact of any kind. Those are all out there already, and you can look them up at leisure. The count of confirmed worlds will have shifted between the recording of this and your hearing of it, because fresh ones are logged every month. The age of Mars's lost magnetism will be sharpened by whatever paper comes after this. The Venus models will be retuned. The reckoning of how much time Earth has left will slide a few 100 million years one way or the other, depending on whose latest run you read. The numbers themselves are not what counts. What counts is the figure they trace once you lay them all down side by side, and the figure runs roughly like this. The cosmos makes worlds. The worlds are each granted a window. A handful of the worlds put the window to use. Most, by everything we can presently tell, never do, though how far we can tell is not very far. The windows swing shut. The worlds carry on existing once the windows have closed, but they go quiet, and across the ages the galaxy silts up with hushed worlds whose windows shut long ago. The few whose windows happen to stand open at the same moment lie scattered through the dark, held apart by gulfs of distance and of time so wide that finding one another is very nearly hopeless, and most of them never will. We are one such world ourselves, right now, tonight, inside a window broader than any single life could ever spend, and yet far narrower than the planet's own long story. We are inside the gift, and it is the only one that was ever offered, and it is, by itself, more than enough. So let the questions loosen their grip now. Let the far worlds keep their own counsel. Let the unread letters go on crossing the dark without you. And let your own small lit room be the whole of the cosmos for the length of one slow breath. The window is open. The warmth is here. There is nothing left to reach for tonight. Let your eyes close, and let the quiet planet go on turning beneath you, and let it carry you the rest of the way down into sleep.